Hi, my name is Irene, and I'll be presenting our paper, BTS, Harmonizing Specialized Experts into a Generalist LLM. This work was done with a wonderful team of researchers at Meta. In the past, scaling up model size have generally led to stronger models, but the simple bigger is better approach has several challenges during pre-training. First, large-scale pre-training demands heavy synchronization across compute clusters. This requires expensive interconnect hardware and causes slow communication. Plus, with more devices, there is a higher risk of hardware failures interrupting training. Second, many domain-specialized models like Code Llama are already available. Pre-training from scratch wastes these existing experts. Finally, there's a data mix trade-off. Improving on a new domain often leads to forgetting the original data. So instead of pre-training larger and larger models from scratch, one promising direction is to train or even reuse many smaller expert models, and then combine these expert models into a single, more powerful generalist LLM. One idea is to train a router that selects a subset of the most suitable expert models for a given prompt. The advantage is that the router is very lightweight, with only a small number of trainable params. It's also highly interpretable because the experts stay frozen, so you can directly see which ones get selected for a prompt. The downside is weaker performance, since there are no learned connections between experts, limiting their expressiveness. Another way to combine expert models is to use them to initialize a larger model, often in MOE architecture, and then continue pre-train for fewer steps. The upside is much stronger performance. But the downside is that the entire model is trained, requiring many more trainable parameters. Plus, since the experts aren't frozen, it loses interpretability. You can't easily tell which expert's knowledge is active. In this work, we introduce Branch Train Stitch, or BTS, a new architecture to combine small expert LLMs into a more powerful generalist model. BTS really gives us the best of both worlds. Training is lightweight. Our experiments use only 300 million trainable parameters. The experts stay frozen, so experts can be added or removed after merging, only retraining the stitch layers. BTS is also highly interpretable. Since the experts stay frozen, you can see exactly which experts are activated and how much they contribute for each prompt. And most importantly, BTS achieves the strongest average performance among all the baselines, despite having very few training parameters. So how does BTS work? BTS operates in 3 phases. The first phase is the branch phase. Following prior works like BTM, we start with a pre-trained seed LLM, such as Llama 3, and create n copies of it. In the train phase, each copy of the seed model is independently pre-trained on a specific domain, for example, code or math data. This gives us specialized expert models. And if some domain experts are already available, like Code Llama, we can skip this step and simply reuse those models. The final stage is the stitch phase, which is the key novelty of BTS. In the stitch phase, we can stitch together the expert LLMs to initialize a larger LLM and then continue pre-train for a really small amount of steps. Let's take a closer look at the BTS architecture. To initialize the BTS architecture, we simply take the existing expert LLM and insert these lightweight stitch layers among them every few layers. Only these stitch layers are trained while the expert models remain frozen. When using the stitch layers to combine representations from multiple experts, there are many possible designs. In principle, every expert could connect to every other expert, or we could restrict connections to only certain pairs, or anything in between these two extremes. In BTS, we use a hub and spoke design that strikes a nice balance between efficiency and performance. The hub is the seed LLM, and the spokes are the experts. We alternate between 2 types of stitch layers, which control the direction of representation updates. In the expert into hub layer, the hub can update its own representation using these experts. The expert's representations are projected into the hub's representation space. The hub then combines its own representation with these projected experts, weighted by a learned gate that decides how much to incorporate each expert. In the hub into expert stitch layers, the update direction is reversed. The experts now update their representations using the seed model. For all of our generalist experiments, we start with a 2.7b parameter pre-trained seed model and create 3 copies. Each one is then continually pre-trained on a specialized data mix, code, multilingual, and math data, to create 3 domain-specific experts. Now, let's look at how BTS and different baselines perform on downstream tasks. First, we see that each expert LLM performs well in its own domain but struggles outside of it. For example, the code expert does well on coding tasks but falls short on everything else. Moving on, we see heavyweight experts perform well but require many training parameters. In our case, they have 7 to 9 billion training params. On the other hand, lightweight methods freeze expert weights during merging, requiring far fewer trainable params, but their performance is weaker since freezing limits the model's ability to adapt or share representations across experts. Finally, BTS gives us the best of both worlds. It achieves the highest average performance across all tasks, even outperforming heavyweight methods with just a fraction of the training params. BTS is also the only method that beats individual experts in their own domains, outperforming the code experts on MBPP and the math expert on the math task. So far, we've looked at how BTS performs within each expert's domain. But a more interesting question is whether merged models can develop new capabilities at the intersection of expert skills. This is what we call cross capabilities. To test this, we look at the following setting. Take a Russian language expert and a math expert. Can we combine them so that the resulting model performs better than either expert alone on Russian math tasks? We find that BTS can indeed leverage both the math and Russian experts to excel at this new cross-domain tasks. Even with the experts frozen, adding these lightweight stitch connections allow BTS to go beyond the sum of its parts. It also achieves the best cross-capability performance among all lightweight methods. Some heavyweight baselines also perform strongly, even outperforming BTS, but this is likely because they have much greater training capacity on in-domain data. Lastly, one of the really nice properties of BTS is that it's highly interpretable. Specifically, we can look at the gate values to understand how much each expert contributes during inference. In this figure, we visualize the BTS gates value across 3 different domains during inference. You'll notice that the specialized experts for each task usually dominates, while still mixing in useful representations from other models. For example, on the math benchmark GSM 8K on the left, the math experts, represented in orange, maintains the highest gate value consistently across both the input context and the generated output. So, to conclude, in this work, we present BTS, a new method for combining independently trained expert models into a single, more capable generalist LLM. BTS achieves the best generalist performance across expert domains while requiring very few trainable params. Also, BTS can develop strong, entirely new capabilities at the intersection of expert specialties. And since the experts stay frozen, BTS is super flexible and interpretable. Overall, BTS points towards a path for building scalable, flexible, and interpretable generalist LLMs. Thank you for listening.